Thermal conductivity was important for Fourier's law in heat conduction, the rate equation. For convection, this H, which we call the heat transfer coefficient, is critical in determining convective heat transfer. So let's make sure we get the terminology correct at the beginning. Thermal conductivity is the parameter that's important for Fourier's law, the material property. H is more than a material property. It's a combination of material and system properties, and it's called the heat transfer coefficient, which is important for convective heat transfer. And the final one, the final rate equation, is the radiation rate equation. Which is given by Stefan Boltzmann's law, which basically says that the heat rate equals this material property we'll talk about, a constant, the area, times the difference of the temperature to the fourth power between the surface temperature, the surface again, and the temperature of the surroundings. So let's stop here for a moment. So the surroundings. So for convective heat transfer, we have the ambient. Ambient is clear. It's the air. It's whatever is immediately around. The water, if you're in a pool, that would be the ambient, the water temperature. But what's the temperature of the surroundings? Well, it's a little bit more complicated, but take this as an example. If you have a hot object in a room and the walls around the room are cold, then the walls of the room would be considered the ambient. Now, the temperature of the walls in a room could be different than the air temperature. I'm sorry, the walls of the room would be the surroundings. So the temperature of the air in the room would be the ambient. Now, a lot of times the air temperature will be the same as the wall temperature, but they don't necessarily have to be the same. So we'll come back to that later, but I just wanted to point out the difference between the surroundings in terms of radiation between an object and walls and the ambient temperature as in convection from the surface of an object to the air or fluid around it. So this material property is known as emissivity. And it basically characterizes the fraction of energy that is allowed to leave a material through radiation in comparison to the maximum amount that leaves, which is the amount that leaves a black body. And we'll talk about what a black body is more when we go into radiation. This constant here is Stefan Boltzmann constant. And it's something you should commit to memory. So this sigma equals 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the fourth. So you want to commit this to memory for this course, Stefan Boltzmann's constant. Now we can do something else. We talked about a heat transfer coefficient for convective heat transfer. It's convenient to define something like that for radiation. So the community has done that. I say the community, the heat transfer community, not your local community. They define HR, this is the radiative heat transfer coefficient, equals emissivity times Stefan Boltzmann constant times a linearized version of Well, I'll write it and then I'll talk about it. So basically, this is defined as the radiation heat transfer coefficient. And what it does when you put it back into the rate equation is it linearizes the rate equation. Working backwards here on the board, this is what we get now. So the thing is that one of the differences, the main difference between radiative heat transfer and conduction and convection is that in radiation you have these temperature to the fourth power terms showing up. And that comes from a lot of work done by Stefan and Boltzmann and Planck. That's why Stefan and Boltzmann, their name is on the constant that's important here. So because you have temperature, the difference of temperature to the fourth power, when you solve these problems, they're nonlinear. So in the attempt to linearize them, and the importance of this will show up later in the course, we define this radiative heat transfer coefficient. So another note here is that because you're taking the difference between the temperature to the fourth power, radiation heat transfer, or the heat rate, becomes significant in comparison to conduction and convection only when the temperature difference is large. So I want you to think about that. Maybe put some numbers in and run through it and just make sure that makes sense to you. That for radiation to be significant in a lot of problems, the temperature difference between the surface and the surroundings has to be very large because of the fourth to the fourth power dependence. So let's go ahead and take a break here.